Welcome to the deep dive. We take stacks of information articles, research notes, and pull out the really important stuff.
Yeah, the key nuggets.
Exactly. And our mission today, well, it's to unpack a really fascinating and frankly pretty crucial area for AI's future.
Which is,
How we're making these powerful, huge AI models, especially transformers, more efficient, more practical.
putting them on an AI diet, you could say.
I like that, an AI diet, because really it's a challenge that comes directly from their own success, right?
Absolutely. Transformers, they're now the backbone for, well, almost everything in advanced AI. Language, image generation, you name it,
But they're massive?
colossal, often. And that size creates huge hurdles for actually using them in the real world. So we're going to dig into how researchers are tackling this.
Head on.
Yeah, with some methods that might surprise you. They're often quite simple, conceptually, but really ingenious.
So if you've ever wondered how these giant AI brains could possibly run on, say, your smartphone,
Or how AI voices might soon sound completely human.
then this deep dive is definitely for you. We're getting into the nitty-gritty, how these models get compressed, distilled, even redesigned.
And we'll look at some really cool real-world examples.
Okay, let's unpack this then. Deep neural networks. They're everywhere in AI now.
Ubiquitous.
But among them, these transformer models, which first showed up around 2017.
Yeah, the attention is all you need paper.
Right. They've really become the dominant choice. NLP, computer vision.
They're the foundation for giants like GPT, Llama, BERT, Clip, VIT. The list goes on.
And their scalability is key.
Absolutely. That lets us build models with billions, I mean literally billions or even trillions of parameters.
Take GPT-3. How big is that one again?
GPT-3 has 175 billion parameters. It needs about 350 gigabytes of memory just to store it.
Wow. 350 gigs. That's a lot.
It's huge. And it's not just the storage. It's expensive to run. It has a significant carbon footprint.
And forget running it on your phone.
Exactly. Deploying on resource-limited devices. Very, very challenging. Which is why model compression isn't just, nice to have. It's essential.
Right. It's a necessity. So this big model problem, or your big appetite problem, how are people tackling it? You mentioned some strategies.
Yeah, several clever approaches. Think of them like different ways to pack a really oversized suitcase.
Okay.
Broadly, we can group them into maybe 4 main categories. Each comes at it from a different angle.
Let's hear them.
First, there's pruning. This is like trimming excess branches off a tree.
Getting rid of spec you don't need.
Exactly.
Yeah.
Directly removing parts of the model could be whole blocks, attention heads, layers, even down to individual connections if they're redundant.
Okay, pruning. What's next?
Then there's quantization. This is about reducing the precision of the numbers inside the model.
Less detail in the numbers.
Sort of. Imagine going from high-def video to standard def, but for the model's weights and calculations. Using fewer bits to represent each number. Shrinks the size a lot.
Makes sense. Number 3.
Knowledge distillation. This is a training thing. You have a big, powerful teacher model.
The expert.
Right. And it transfers its knowledge, its expertise, to a smaller, more efficient student model. The student learns to mimic the teacher.
Ah, learning from the master. Okay, and the last one.
The fourth is efficient architecture design. This is more fundamental.
So not just shrinking the existing thing, but building it differently from the start.
Precisely. Rethinking the transformer's internal structure to make it inherently lighter and faster. Designing for efficiency from the ground up.
Okay, 4 strategies. Pruning, quantization, knowledge distillation, and efficient design. Let's dig into quantization first. That idea of using fewer bits seems really powerful.
It really is. The impact can be pretty dramatic. For instance, taking a standard model using 32-bit floating point numbers.
Full precision, basically.
Right, and quantizing it down to 8-bit integers. That cuts the memory cost by 4 times, instantly.
Factor of 4, just like that.
Just like that. And not just memory. It lets models run much faster on specialized hardware that's optimized for this low-precision math.
Okay, but how do you actually do the quantization? You mentioned 2 ways.
Yeah, 2 main flavors. There's post-training quantization, PTQ. You train the model normally, then you quantize it afterwards, tweaking the parameters.
Retrofitting it?
Kind of. And then there's quantization-aware training, or QAT. Here, the training process itself knows about the quantization. It learns while accounting for the lower precision.
Ah, okay. So it's built in from the start of training. But the big question, always, is accuracy, right? How much performance do you lose?
That's the core trade-off. And it depends. For large language models, PTQ can struggle, especially with what we call outliers, extreme values in the data. That often leads to a noticeable drop in performance.
So PTQ can be tricky for LLMs. What about QAT?
Well, this is where it gets interesting. With QAT, sometimes models can actually perform better than the original full precision ones.
Better. How does that work?
It's a bit counterintuitive.
Hmm.
But it seems like the constraint of lower precision during training forces the model to learn more robust representations.
Yeah.
Like it has to be more efficient with its resources.
So the limitation forces a better solution in a way.
It can, yeah.
Hmm.
QAT often lets you tap into the true potential accuracy of a quantized model more effectively. But there's a limit.
Ah.
When you push to really low bit widths, like 4-bit quantization,
Yeah.
you often see a significant performance drop. Even with QAT, it's a very delicate balance.
Finding that sweet spot between compression and performance. Okay, that's quantization. What about knowledge distillation? The
How?
teacher-student thing.
The analogy holds up well. You've got your big expert teacher model.
Like a huge GPT model.
Could be. And then you have a smaller student model. The student learns by trying to replicate the teacher's outputs, or sometimes even its internal states. It's reasoning.
So it's learning how the teacher thinks, not just what it says.
Sometimes, yes. We see this in NLP. Models like DistillBERT. It's a smaller BERT trained by the original BERT. Or MiniLM, which specifically mimics BERT's attention patterns and value relationships.
Okay, that works if you have the teacher model. But what about those giant closed models, like, say, GPT-4, where you only interact with it through an API? You can't see inside.
Yeah, that's a huge challenge. But researchers have gotten clever. They've developed something called API-based knowledge distillation.
Learning from a black box.
Essentially, yes. The student model learns just from the outputs the black box teacher generates, maybe instructions, explanations, examples.
So the student learns by studying the teacher's answers, even without seeing the teacher's notes.
Exactly. It's crucial for leveraging the power of those massive proprietary models when you don't have direct access. But it's not without its own difficulties.
Like what?
Well, the training process for KD, even API-based, can still demand a lot of GPU memory, especially for things like computer vision, where you have large image inputs.
Right, processing all that data.
And also, choosing the right teacher is still an open question. Should it be another transformer? Maybe a convolutional neural network, CNN, for vision tasks. That's active research.
Okay, so distillation is powerful but has its own demands. Let's move to pruning. This sounds the most straightforward, just cut out the parts you don't need.
Yeah, in principle, it sounds simple. Just chop off the redundant bits.
Is it really that simple?
Well, there are different ways to prune. You can do unstructured pruning, removing individual weights or connections. That makes the model file smaller, but often doesn't speed things up much on standard hardware.
Why not?
Because the pattern of remaining connections is irregular, and hardware likes regularity. So structured pruning is often preferred.
Which means removing.
Entire components, like whole attention heads or layers or blocks within layers. That maintains a regular structure that hardware can actually accelerate.
Ah, so structured pruning gives you real speedups, not just smaller size.
Often, yes. And the surprising thing is how much you can prune. These huge models often have massive redundancy. You can sometimes remove a huge percentage of parameters without hurting performance much, or sometimes even improving it slightly by removing noise.
Really? Improving it?
Yeah, by forcing the model to rely on its most effective pathways.
Okay, for the big language models, what's a standout pruning technique?
For LLMs, something really impactful is context and token pruning.
Context and token, meaning the input text.
Exactly. Remember, the cost of running a transformer grows quadratically with the input sequence length. Longer text means much, much slower processing.
Right, the infamous quadratic complexity.
So techniques that can prune the input itself, identifying and removing less important words or tokens from the context before feeding it to the main model, are vital.
How effective is that?
Remarkably effective. Some methods show you can prune up to 80% of context tokens for models like GPT-2 with almost no degradation in the quality-metric perplexity.
80%, that's huge for dealing with long documents or conversations.
It's a potential game changer, absolutely.
Okay, so pruning is about removing redundancy. But what about that fourth category, efficient architecture design? Going back to the drawing board.
This is where things get really innovative, I think. It's about fundamentally changing the transformer's building blocks.
Like the attention mechanism itself.
Exactly. That quadratic attention is the bottleneck for long sequences. So people have developed alternatives. Sparse attention, linear attention, multi-query attention, all trying to reduce that complexity from quadratic down to linear or near linear.
Making it scale better with longer inputs.
Precisely.
Yeah.
And there are other optimizations too, like flash attention, which doesn't change the math, but optimizes how it uses GPU memory to make it much faster in practice.
But are people looking beyond attention entirely? Completely new ways to build these sequence models?
Oh, absolutely. This is a really hot area. We're seeing the rise of models like RetNet, RWKV, and Mamba.
Okay, never heard of those. What are they?
They generally fall under the umbrella of state space models, or SSMs. They borrow ideas from older recurrent neural networks using a recursive way to generate outputs.
Like RNNs, weren't they replaced by transformers?
They were, largely because transformers were easier to parallelize for training. But these new SSMs combine the recurrence idea, which gives them linear complexity for inference, great for long sequences.
Linear, not quadratic. Big difference.
Huge difference, and they found ways to make the training highly parallel too. Mamba, especially, has shown great results on text, focusing on modeling discrete, dense information effectively.
So potentially the best of both worlds. Linear scaling and parallel training.
That's the promise. And it's
Oh.
not just attention. People are rethinking the other main part of the transformer block, the feed-forward network.
How so?
One big idea is mixture of experts, or MOE. Instead of one giant FFN, you have many smaller expert FFNs.
A panel of specialists.
Exactly. And for any given input, the model only activates a few relevant experts. So you can make the total model size enormous, but the compute cost for any single input stays manageable.
Clever. More capacity without proportionally more cost per inference.
Right. And even smaller things like using specific activation functions. SWI-GLU is one that pops up a lot, can give noticeable quality boosts for the same amount of compute.
Fascinating. So much innovation happening at the architectural level. This feels like it connects to something you mentioned earlier, residual quantization. You said it links different applications.
Ah, yes. RQ, residual quantization, or sometimes called stacked quantization. It's a great example of a core technique popping up in different places.
Where did we see it first? Image generation.
It made a big splash there, yeah.
Eh.
Generating high-res images efficiently was tough. Older methods using vector quantization, or VQ, they struggled. To get good image quality, they needed a huge codebook, basically a dictionary of visual patterns. But making the codebook huge makes the model slow and unstable. And if you use short codes for efficiency, the image quality suffered.
The classic trade-off again. How does RQ help?
Okay, so there's this framework called RQ Transformer. The first part is RQVAE. It uses residual quantization. Instead of one giant codebook, it uses a single, shared, smaller codebook multiple times, iteratively.
Iteratively, like layers.
Exactly. It approximates the image features in a course-defined way. Layer by layer, it refines the representation using the same small codebook. Imagine painting. First broad strokes, then details, then finer details, all using the same small set of paints.
So you get detail without needing a million different paints.
Precisely. This lets it represent, say, a 256 by 256 image using a much smaller feature map, like 8 by 8, but with multiple layers of these discrete code stacked on top.
And a smaller feature map means?
Less work for the next stage. The RQ transformer itself just learns to predict these stacked codes.
And the result?
Big speedups, generating images 4, 5, even 7 times faster than older models like VQGN, and often with better, state-of-the-art image quality. It was a real leap in efficient image generation.
Wow, okay. Faster and better through layered quantization. Now, how does this same idea, RVQ, residual Vector Quantization, apply to making AI voices sound human? You mentioned CSM.
Right, conversational speech models, CSM. This is where companies like Sesame are pushing the boundaries. They're using RVQ to capture that elusive quality of voice presence.
Voice presence, meaning it feels like you're talking to a real person.
Yeah, that feeling of nuance, understanding, naturalness, moving way beyond robotic text-to-speech.
Well, what was wrong with traditional TTS for conversation?
They often lack context. They generate speech sentence by sentence without really understanding the flow of a conversation. CSM treats it differently as an end-to-end multimodal task.
Multimodal, text and audio.
Text and audio history, yes, using transformers, but crucially operating as a single-stage model for efficiency and better expressivity. And RVQ is key to how it handles the audio.
How does RVQ work for audio?
It uses RVQ to generate different kinds of audio tokens. There are semantic tokens. These capture the speaker invariant stuff, the core meaning, what's being said.
Good content.
Right. And then there are acoustic tokens. These capture the fine-grained details, the speaker's unique voice, the timbre, the emotion, the prosody. RVQ breaks the complex audio waveform into these manageable layered codes.
So semantic layer first, then layers of acoustic detail using RVQ?
Essentially, yeah. They use two main transformer parts. A multimodal backbone looks at the text and audio history to predict the first layer of RVQ codes, the 0th codebook. Then a smaller audio decoder predicts the remaining RVQ codebooks, adding all that richness and detail.
Stacking the codes again, like with the images?
Exactly the same principle. And they use the smart training trick, too, compute amortization, to handle the high memory cost. They train the detailed decoder part on just a subset of audio frames at a time.
Spreading the computational load.
Right. It preserves the fine details without slowing training down to a crawl.
So the goal is digital companions that sound natural, have consistent personality, maybe even emotional intelligence. How close are they?
Well, objective tests like word error rate are near human levels. They're developing new tests for things like subtle pronunciation and understanding context. But
There's always a but.
yeah. The objective tests where humans listen, people still notice the difference, especially in conversation.
How so?
When listeners have the conversational context, they consistently prefer real human recordings. It suggests that maybe the basic naturalness of the voice sound is getting pretty good, almost saturated.
It sounds human enough in isolation.
Right. But the appropriateness of the rhythm, the intonation, the pauses, the prosody within the flow of a real back-and-forth conversation, that still needs work.
Making it react naturally to what was just said.
Exactly. The next frontier is models that implicitly learn those dynamics, turn-taking, pacing, reacting emotionally in context, not just generating perfect-sounding isolated speech.
Fascinating. Okay. Beyond these big pruning, quantization, distillation, new architectures, and this cool RVQ application, are there other specialized tricks for efficiency?
Yeah, definitely a few others worth mentioning. Well, there's tensor decomposition. This is about taking the big matrices, the tensors, that store the model's parameters.
The core math structures.
Right, and breaking them down into smaller interacting matrices. It's a mathematical way to reduce parameters in computation.
Okay. Tensor math tricks. What else?
Early exiting. This is pretty intuitive. The model processes an input layer by layer, right?
Yeah.
With early exiting, if the model becomes confident enough in its prediction after just a few layers, it can just stop. It doesn't have to run through the whole network.
Saves compute for easier inputs.
Exactly. Dynamically allocates resources. And another clever one, especially for generation, is speculative sampling.
Speculative. Sounds interesting.
It speeds up decoding, like when an LLM writes text. Normally generates one word, then the next, then the next. Speculative sampling tries to generate several words ahead in parallel, often using a smaller, faster draft model.
It guesses ahead.
Sort of. It generates a draft sequence, and then the bigger main model checks it very quickly. If the draft is good, you accept the whole chunk, saving time. If not, you fall back. And it can even be done in a lossless way, mathematically guaranteeing the same output distribution as the original slow model.
Wow, faster generation without changing the final output. Clever.
Yeah, it shows efficiency isn't just about shrinking the model, but also optimizing how you use it.
Okay, so pulling this all together, we've got pruning, quantization, distillation, entirely new architectures like Llama and SSMs, specialized techniques like RBQ, tensor decomposition, early exiting, speculative sampling. It's a whole toolbox for making AI leaner and faster.
It really is. And crucially, these methods aren't mutually exclusive. They can be combined.
Stacked, like the RVQ code.
Exactly. A common pipeline might be: start with an efficient architecture design, then prune it to remove redundancy, then quantize it for the target hardware.
And where does distillation fit in?
Knowledge distillation can be used during the fine-tuning stages of pruning or quantization-aware training. It helps the smaller, compressed model retain the capabilities of the original large model.
So they work together synergistically, but what are the big remaining hurdles? What's still hard?
A major one, ironically, is the cost of compression itself.
Compressing is expensive.
It can be. Retraining a pruned model or doing that intensive quantization-aware training, that can still require massive amounts of computation, sometimes nearly as much as training the original giant model in the first place.
Huh. So you save costs at inference time, but the compression process itself is costly.
Right. So finding training-efficient compression methods is still a huge priority, making the diet plan itself less expensive, basically.
Makes sense. Any other big frontiers?
Definitely continuing to explore architectures beyond the transformer. Those recurrent models like RetNet and Mamba, with their linear complexity, are really promising for long sequences. And even simpler things like pure MLP, multi-layer perceptron architectures are being revisited for vision tasks. Maybe we don't always need the complexity of attention.
Going back to simpler building blocks, but making them work better.
Potentially, yeah. Lots of exciting avenues.
Okay, this has been a fantastic deep dive into the world of AI efficiency. Before we wrap up, what's one provocative thought you'd leave us with based on all this?
Well, if these compression techniques and these novel architectures keep improving at this pace, making powerful AI much more efficient and accessible, what kinds of applications, things we can barely imagine right now, might become totally commonplace in just the next few years? How might that truly transform our daily lives?